Lesson 1.5, Greatest Common Factor. In this lesson, you will use diagrams to identify common factors and then find greatest common factors. Factors that are shared by two or more numbers are called common factors. The greatest of the common factors is called the greatest common factor, GCF. One way to find the greatest common factor of two or more numbers is by listing the factors. Example 1, finding the greatest common factor using lists of factors. Find the greatest common factor of 24 and 40. So I'll start with 24. And I will record my factor pairs. So starting with the first whole number, 1. 1 times 24 is 24, and I'm going to bridge those two together. Those are factor pairs. The next number is 2. I know 2 goes into 24 12 times. So 2 and 24 are a factor pair. 3 goes into 24 8 times. So they are a factor pair. And 4 goes into 24 6 times. The only other whole number left would be 5, and 5 is not a factor of 24. So those are my factors for 24. Following the same process for 40, I have 1 and 40, 2 and 20, 3 is not a factor of 40, but I know that 4, connect 2 and 20, 4 and 10 are factor pairs, 5 and 8, and then the numbers that are left are 6 and 7, and neither of those are factors for 40, so those are the factor pairs for the number 40. The next step is to go back and circle all the factors that they have in common. So they both have a 1. They both have a 2. There's a 3 here in 24, but not in 40, so I will not circle 3, but they do both have a 4. 40 has a 5, but 24 does not, and 24 has a 6, but 40 does not. They both have 8. And then there's a 10 in the 40, a 12 in the 24, a 20 in the 40, a 24 in the 24, and a 40 in the 40, though none of those match. So now I need to go back and look at the ones I've circled, which is the greatest. And it's clear to see that the 8s are the greatest factor they have in common. So the greatest common factor of 24 and 40 is 8. Example 2, finding the greatest common factor using prime factorizations. Find the greatest common factor of 12 and 56. Make a factor tree for each number. In example 1, we found the greatest common factor using lists of factors. This is another way to find the greatest common factor using prime factorization and a factor tree. We'll start with 12. And remember, this is where we make the branches, so I'm going to start with 2 and 6. 2 is prime, so I'll circle that. 6 is a composite number that I can break down into 2 times 3, which are both prime numbers. So an easy factor tree for 12. Doing the same thing for 56 over here. I'll break that down into the basic fact of 7 times 8. 7 is prime. It has only factors of 1 and 7. But 8 I could break down into 2 and 4. 2 is prime. And I could break the 4 down into 2 and 2. And there's the factor tree for 56. The next step then is to write the prime factorization for each number. So for 12 I have 2 times 2 times 3. And for 56 I have 2 times 2 times 2 times 7. Now I need to circle the common prime factors. So they both have a set of 2 there, and they both have a set of 2 there. The other factors that are left don't have any in common. Now I need to find the product of the common prime factors. 2 times 2 is 4. The greatest common factor of 12 and 56 is 4. Example 3, finding two numbers with a given common factor. Which pair of numbers has a greatest common factor of 15? So now we're given the common factor, the greatest common factor, and we need to find which pair of numbers would have that 15 as its greatest common factor. We could go through each of these choices, A, B, C, and D, and list the factors for each of those two numbers in each problem and check to see which one has the greatest common factor of 15. But before we do that, we could use some of our prior knowledge to eliminate some of the choices and reduce the amount of work we have to do. For example, A says 10 and 15. Well, what you know about factors should tell you that 15 cannot be a factor of 10 because 10 is a smaller number. There's no whole number times 15 that's going to get you 10. So right away we can eliminate question A, or answer A. And then thinking back to our divisibility rules, we know that 15, because it ends in the ones place with a 5, the numbers that are going to be multiples of 15 also have to have a 0 or a 5 in the ones place. So answer B, 30 and 60, both meet that criteria. They both have a 0 in the ones place. However, on answer C, 21 has a 1 in the ones place instead of a 0 or a 5, so we can eliminate that choice. And then D has a 5 in each of those two in their ones place, so those could also be a possibility. Now we've cut our work in half. We have only choices B and D to investigate. So let's start with B, factors of 30. I'm going to make a list of factors of 30. Starting with 1 and 30. Join those two together. 2 and 15. 3 and 10. 4 is not a factor of 30, but 5 times 6. And since those numbers are right next to each other, there are no whole numbers left. So that is the complete list of factors for the number 30. Looking at the factors of 60, I have 1 in 60. 2 and 30. 3 times 20. To join those two. 4 and 15. 5 and 12. 6 and 10. And 7, 8, and 9 are not factors of 60. So that is the complete list for factors of 60. Looking at then the factors and circling the ones they have in common, we have a 1. They both have 2. They both have 3. They both have a 5. And a 6. A 10. A 15. And a 30. The greatest common factor of 30 and 60 then is 30. That leads us to believe that D must be the correct answer, but we can't just assume that, we have to prove it. So let's make that factor list for both 45 and 75 and see if we can verify our assumption. Factors of 45 would be 1 and 45. 2 is not a factor of 45, but 3 times 15 is another factor pair. 4 is not a factor of 45, but 5 times 9 is another factor pair. And 6, 7, and 8 are not factors for 45. So that is our complete list, 1, 3, 5, 9, 15, and 45. Same process for 75. We have 1 and 75. 2 is not a factor of 75, but we have 3 and 25. 4 is not a factor of 75, but we have 5 and 15. 6, 7, 8, 9, 10. None of those are factors of 75, so that is our complete list. Going back now and circling the ones in common, they both have a 1. They both have a 3. They both have a 5. No 9 and 75. They both have a 15. And that is the greatest number they have in common. So 15 is indeed the greatest common factor for the numbers 45 and 75, which means our answer would be D. The greatest common factor of 45 and 75 is 15. Example 4, a real-life application. You are filling piñatas for your sister's birthday party. The list shows the gifts you are putting into the piñatas. You want identical groups of gifts in each piñata with no gifts left over. What is the greatest number of piñatas you can make? The list shows that your resources include 18 bottles of nail polish, 24 pairs of earrings, and 42 lollipops. The greatest common factor of the numbers of gifts shows the greatest number of identical groups of gifts you can make with no gifts left over. So to find the number of piñatas, we need to find the greatest common factor. To do that, let's make a list of the factors first. So 18 bottles of nail polish. 18, the factors would be 1 and 18. 2 and 9. 3 and 6. And let me partner those up to make sure I have them all. Okay, for 24 pairs of earrings, the factors would be 1 and 24. Partner it up, 2 and 12. 3 and 8. And 4 and 6. And for 42. 1 and 42. 2 and 21. 3 and 14. No factors for 4, 5, 6, and 7. So there are my factors. Now circling the ones they have in common, they all have a 1. They all have a 2. I see a 3 in each set. There's only a 4 and 24, but there is a 6 in each of them. There's only a 7 in 42, only an 8 in 24, only a 9 in 18. 18, 12, 21, 24, and 42. All the rest of the numbers are different. So the greatest common factor are the 6s. So the greatest common factor, the most groups of piñatas you could make with none left over, would be 6.